This is OChem 1 with Professor Rainier. This is Anthony Barbiero and Eric Batista, and we're going to talk about asymmetrical and symmetrical reductions.
And if you're not sure what a reduction is, it's just the addition of hydrogens to the pi system. Here we have an alkene reacting with hydrogen gas and palladium.
The palladium on the carbon is there acting as a catalyst so that this reaction can actually happen.
So this reaction is going to occur with a syn addition of the hydrogens. In other words, they're going to add to the same side of the molecule. So here I have them coming to the inside the paper.
This basically does the same thing as the conversion of an alkene to an alkane. You just take two equivalents of hydrogen gas still with palladium and carbon as a catalyst. So first, when you add the hydrogen to the pi system there, you create a double bond, and it's just like above. The hydrogens will react with the pi system in a syn addition, and the second equivalent of H2 is then added because once this starts, it's going to keep going with this catalyst, and you end with this as a product overall.
Alright, so here we have alkynes to cis alkenes. And here we cannot use palladium on charcoal because it's too reactive to react with only one equivalent of hydrogen gas. So instead we're going to use a Lindlar catalyst, which consists of palladium on calcium carbonate with lead acetate and quinoline. This allows for the stoppage of the reaction after one syn addition. So here's what's going to happen. It's going to have your hydrogen gas and your Lindlar catalyst. And it's going to be yet again a syn addition of the hydrogens to form a cis alkene.
And because palladium on carbon is too reactive of a catalyst and will only make syn addition of the hydrogens, what we have instead is sodium metal dissolved in an ammonia solution. And because of time, we're not going to go too in depth on the mechanism, but what happens is the product formed is a trans addition, because when the sodium is put into the ammonia solution, the mechanism allows it for radical intermediates to be formed to allow for this trans addition to happen.
So the asymmetrical reductions include epoxides and alkyl halides. For epoxides, it's basically a nucleophilic attack where LiAlH4 has a hydride that can act as a nucleophile and attack the less substituted carbon and break that epoxide bond. The oxygen that is then holding the negative charge is then protonated by the water in solution.
And the second one is alkyl halides. This does basically the same thing with a nucleophilic attack, but what it does is it does it in an SN2 fashion, as shown. So as the leaving group leaves, the hydride comes in and replaces to make that.
And that concludes asymmetrical and symmetrical reductions.